we're going to run a hypothesis test using what's called a p-value. The picture is this. There's a claim made about some parameter. For example, maybe the status quo, the way things have been for some time, is that the mean of some population is 170. Okay, I'm just making this up. Is 170. But now, maybe because something in the process has changed, it's thought that the mean has increased. To test the claim that the mean has increased, a random sample, suppose a random sample is taken and produces a sample mean of 172.52 and a standard deviation of 10.31. So we want to test the claim that the mean has actually increased. Now there is an apparent increase right here. I mean, the way things have been is that the mean is 170. We take a sample and we get 172.5. So there is an apparent increase, but what we really want to know is that apparent increase real, maybe due to some real factor like a change in the process, or is it just due to chance variation in the sample that we took? So to run our test, the first thing we're going to do is we will state the null and the alternate hypotheses. So step 1, get the null hypothesis. H naught states that mu, I'm going to leave that blank just for a second. Alternate hypothesis, H sub A, I use A for alternate, states that mu is, now the way things used to be, status quo is that it's 170. We think things have changed. So we're going to write this as greater than 170. Now in step 1, I'm going to have mu, and then I'm going to have the 170, but to have it mathematically correct, I'm just not going to say that it's equal to 170. What I've got here is that it's greater than, so what is the opposite of greater than? The opposite of greater than is that it could be equal to or it could be less than. So sometimes you'll see this hypothesis written like this, maybe mu equals 170, but just to be consistent mathematically, we're going to make these two completely the opposite. So when you set these tests up, you might want to think about what it is you're doing, write that one first, and then this one here, the null hypothesis will always have an equal sign in it. Now next up is we're going to obtain a random sample from the population and compute the corresponding sample statistic. So what we're testing up here is a mean, so we're going to compute the corresponding statistic, which will be X bar. Now if we were doing a proportion, if we were testing a proportion, we would be computing P hat. So now the question that we're going to have is this. So in our example, we're going to ask, what is the probability of observing this value here if mu really is 170? So if the mean of the population truly is 170, how likely is it that we're going to take a sample and get 172.5? Now if we decide that it's unlikely, then we're going to reject H naught. This makes sense because we are actually observing this value. And we're saying that observing this value is unlikely. And typically, we don't believe that we see unlikely events. So we're going to go with this one and reject the H naught. And then if we decide that seeing this number here is not unlikely, then we will not reject H naught. This should make sense too, because if the mean really is 170, and we observe this value right here, and we're saying seeing this value is not unlikely, then we're going to think, okay, I'm not going to reject this because I'm seeing something that is likely. Now, just what do we mean by unlikely and not unlikely? This is where the p-value comes in. So let's take a look at an example. We'll just continue our example and talk about the p-value as we do this. So here's what we have so far. Step 1, we have that H naught states that mu is, we're going to say, less than or equal to 170. Step 2 was our alternate hypothesis that the mean is now increased, is greater than 170. And the information that we got was that X bar, right, when we took our sample, X bar was 172.52, S was 10.31. Now, I'm just going to tell you what this here is in this case, okay? And we'll see how to get it soon. In this case, the p-value is 0.117, 0.117. We'll see how to get that shortly. Here's what this p-value means. A p-value of 0.117, that means that if mu truly is, it really is 170, that we would expect to see a sample mean of 172.52 in about 11.7% of our observations. So if we were to make observation after observation, sample after sample after sample, how often would we see this value come up, the 172.52? How often would we see that appear if the mean really was 170? Well, we're saying that we would expect to see it about 11.7% of the time. What we need to decide then is if there is an 11.7% chance of observing some event, do we think that that event is unlikely to occur or not unlikely to occur? Now, I'm saying unlikely and not unlikely. You might think of not unlikely as being likely, but this is a better phrasing, as we'll see later. So that's our question. If there's an 11.7% chance of observing some event, do we think that that event is unlikely to occur or not unlikely to occur? This decision, this is completely up to the statistician, right? It's your call. But fortunately, there are some agreed upon guidelines. The guidelines involve that value alpha. You remember alpha? I've just popped it back in here from our discussion in the last unit. But alpha, that's the probability of making a type 1 error. Now let's just remember what that is. Alpha is the probability of making a type 1 error, and if we let alpha be 0.05, that means we have a 5% chance of rejecting a true claim. Now if we let alpha be 0.01, then we have a 1% chance of rejecting a true claim. And alpha, that's called the level of significance, and it's the probability of rejecting H0 when it's really true. So alpha, the level of significance of a test, is the probability of rejecting a true hypothesis. To help us decide if a given p-value indicates that some event is likely or unlikely, then we compare p to alpha. Now here's an example. So suppose in our hypothesis test we compute the p-value, which we'll do soon, we compute the p-value to be 0.117. Now we set alpha. So suppose that we set alpha to be, say, 0.05. Well, this means that 5% is our boundary for belief. We will consider an event to be unlikely to occur if the probability it occurs is 5% or less. So if there is only a 5% chance that some event can occur, we're going to consider that event to be unlikely. But if it can occur more than 5% of the time, we'll say it's not unlikely. So let's compare p to alpha. I like to do this by drawing a little table. So here's my p and alpha. Now the p is 0.117, alpha is 0.05, and we can all see that 11.7% is greater than 5%. So our p value is greater than the alpha value. The p being 0.117, that indicates that we expect to see some event about 11.7% of the time. This is more often than our boundary value of only 5%. So we conclude that this event is not unlikely. So all the way back to the beginning now, here's what we were looking at. We had our base value of 170, right? That was the status quo value. We took a sample and we got X bar to be 172.52. Now our p-value indicated that it was not unlikely to see this if this is true. So given that this is true, our p-value showed this is not unlikely. So statistically, what we say is there is no significant difference between these two values. And now if there's no significant difference, that implies that we do not reject H naught. Right? There's really no difference between the 172.52 and the 170, so we don't really have enough evidence to say that the mean has increased in value. So we're not going to reject H naught. So as we do these problems, what it comes down to is you have to be able to determine when do you reject, when do you not reject. So I always look at it like this. If there's no significant difference, I do not reject. No significant difference, do not reject. If there is a significant difference, then reject. Here's another quick example. Suppose that you compute the p-value, which we'll do soon, to be 0.0086, and you choose alpha to be 0.01. Now, you're going to compare p to alpha. All right, here's my little table, p and alpha. Now, the p is 0.0086, alpha is 0.01. Now, 0.0086 is less than 0.01. So p is less than alpha, and p being 0.0086 indicates that we expect to see some event about 0.86% of the time. That's less than 1% of the time. This is less than our boundary of 1%, so we're going to conclude that this event is unlikely. So when we run these tests and we get our p-value, we have to have some way of remembering what does that p-value tell us to do, reject or not reject. So here's how I think about it. The smaller the p-value, the less likely the event. And less likely to me means that it's unlikely. And if it's unlikely, that means it's unlikely I will see it, and I'm going to reject H naught. Here's what you see in every book. If p is less than or equal to alpha, you reject H naught. If p is greater than alpha, you fail to reject H naught. Now, when doing these tests, we never say that we accept H naught. All right? We never accept H naught. Statisticians are always skeptical, and instead of saying accept H naught, they just say they do not have enough evidence to reject H naught. They fail to reject H naught. So let's just summarize it this way. Here's how I remember all this. Less than or equal to. Less than or equal to, that looks like small to me. So a small p means p for probability. Small p, small probability. If it's a small probability, it's unlikely. And if it's unlikely, I'm going to reject. And similarly, if p is greater than alpha, okay, I see the greater than sign. I think large, big, or high. High p, high probability. It's a high probability, it's not unlikely, and if it's not unlikely, I'm not going to reject. So that'll do it for this section here. Now in the next section, I'm actually going to show you how to find these p-values.